It is indeed my 5th time, maybe 6th time, I'm not sure. I was here, I think, 2016 the first time. There was really like an addiction back then to travel, and then there was COVID, and then somehow it got out of the common routine for me to attend conferences, but this one is a special one. So things changed. I got some white hair here, so I have a solution to, still you look young and cool, but some things don't change, and that is the vibe of this conference. This is just way too good, way too amazing to miss. So very good to see everybody here again in Florence after so many years. So that's unfortunately generated by Midjourney. I've never been that cool, but these are the facts about me. I live in Munich, Germany. I organize an event there. I made PyCon Germany in 2016. I made PyCon Web. Some of you have been there. I saw the faces in 17 and 18, and then COVID killed it. And I'm running an agency. The agency is called Tech5. It's not really a proper agency. It's more like a bunch of friends working together and having no business plan whatsoever. But I mean, as long as we do good stuff, people continue ordering. So that's a business idea. Now, going back to the topic, we are speaking about AsyncIO together. This is such a trendy topic for the last 5 years or so, I think. When I prepared the presentation, I looked on YouTube videos of PyCon US, EuroPython, not to repeat myself too much, but it's impossible because all of these things are covered by so many great speakers. So I had to rework my plan a little bit, and it's also difficult to adjust to different level of expertise of the big crowd. The bigger it is, the harder it is. So if I'm getting too much in details or too much on the surface, I hope I will correct this on the fly. I have plan A and plan B for this, but I still try to make this more interactive. We will have some general overview, as well as we will have some codes, and we will hopefully understand it together and look for problems and see how that can be addressed. So what is the revised plan for this talk? We have just 25 minutes. It's not much. In these 25 minutes, I'm going to squeeze the coordination of concurrency. These are the basic things. I'm talking from experience, especially because of working with my clients in Germany. There are good developers working for the clients. Sometimes they just never reach to that point of documentation where simple things to coordinate concurrency and AsyncIO can be done in native AsyncIO tools. Sometimes you just never got to know that. And once you see it one time, this is enough, this talk is enough. You see it one time, you will hopefully use it. Half of you already use it probably, but a half not, so I guess it's worth another recap. Now, next topic is a more painful one. It's error handling. And nobody really knows how to do it right. So this is a subjective matter, and I will show things not to do and things that do work for me most of the times. And finally, a couple of words about debugging. Debugging is a whole new topic. I think there was a previous speaker, Andriy Soldatenko. He made 2 years ago a really good talk about debugging. You can look it up online and just watch it if you want more details. I'll give you just a little glimpse on that. Good, let's start. The first on the list is concurrency coordination. So our programs grow more complex, and with multiple asynchronous tasks, it becomes difficult to manage how these tasks interact, especially when they do have access to the common resources. Of course, the most common one would be a database, and they need to operate in a specific order accessing that resource. These tools are also called synchronization primitives, more scientific way to call it. And I'm speaking about this logs, event, conditions, and semaphores. There are more, but out of this scope. So we will discuss how these tools help to maintain data integrity and how to keep the order of execution of concurrent tasks. This is essential because the bigger and more complicated our application gets, the more you see chaos by not structuring it properly. The first on the list is logs, and I'm sure most of you know what is logs, so I will not go in details about the theory. However, there is AsyncIO log, and not everybody knows that. It's just like that, asyncio.log. Look at this code. I think it's self-explanatory, but I will still go over it. This context manager async with log, this is a really simple way to ensure that the statement of that block is only accessed by one coroutine at a time. So you need to make sure a piece of code is not executed in parallel, like under no circumstances. Access to common resource, cache update, database update, whatsoever. Just this line on top, async with lock, does the job. Next, events. So this is for coordinating coroutines with signaling, and the use case is when we need to notify one or more coroutines of a specific condition or the event that has occurred. So they act kind of like a signaling mechanism that allows coroutines to wait for certain activities to be completed before further processing. So how events work, let's see. So event object maintains an internal flag which can be set to true with the set method that we see over here. And as you can guess, the wait method makes us wait for something to be set. So once the event is set, all coroutines waiting for it are awakened simultaneously. This is also a very practical thing to have when we need a simple blocking. So getter, one piece of the software is waiting, another piece of the software runs set, and the flow is resumed. So this is really a very, very basic way to ensure the correct order of execution of your coroutines. Now going a bit more deep into AsyncIO conditions. So it's the same, but they wait for specific conditions to be met. I'll show you the code now, and the condition object combines the functionality of what I previously showed you, the lock and the event. It has methods like you see here, wait for coroutines to pause until the condition is notified, and you have methods like notify and notify all to wake coroutines that are awaiting. So conditions also support ownership management through a lock that can be used to synchronize access to shared resources. Let's look at the code. So it is using context manager similar to the locking mechanism, as you see on the top. Consumer makes async with condition. Then condition wait is something similar to the event that I showed, but now it's like combined in one thing. And the second function, asynchronous function, is a producer that is making explicit notification in the last line over here to wake up all consumers waiting for this condition. That's like 101 about this mechanisms. How can you control your flow really easy? I will repeat, it's locking, it's events, and it's conditions. Really simple stuff. Mark it, note it somehow. If you didn't use it, this is the simplest way to ensure that your coroutines are made in the correct order. Now we rush to the next topic, error handling. This is a painful one because every experience here is made with kind of a blood or a client blood or your face in blood after some failure. For this, we want to have a better metaphor. Typically, in Italy, they use cooking as a good metaphor for running asynchronous tasks. Like you cook in the kitchen, you do many things at the same time, you switch from one task to another. This is a typical one, it's boring. So I propose airport baggage claim mechanism. It has concurrency in operations, because just like async tasks in programming, where multiple functions run concurrently, baggage system processes multiple bags simultaneously. So arrival and distribution of the bags on the carousel are handled efficiently without waiting for the individual processes to complete. Then it's event-driven, obviously, because when the flight arrives, like you put the luggage on the belt. It's non-blocking, and exceptions do happen because we all have lost our luggage. Let's see about the naive approach. How would like a person just reading a tutorial of AsyncIO implement it? So what do we have? We instantiate a queue object, we get an IO loop, and then we create a task to put something on the belt on the airport, and then we create a task to get things from the belt. Let's assume these are independent coroutines that just run in the background. One part is putting things on the belt, another part is taking things from the belt. Then we run an endless loop that runs forever, and yeah, finally, of course, some baggage has to be lost, so we are losing it and closing the loop. What's wrong here? There is absolutely no error handling. There is absolutely no error handling, and I will show you the first iteration. I usually see is something like except block there with keyboard interrupt. That is when the software is stopped. What is the problem of catching keyboard interrupts? Anybody? Yeah, half of you know that. Tell me, what's the problem with catching keyboard interrupt exception? Okay, then I just say it. This only happens when you debug. So when you run the code, so many people write catching the exception, meaning when the software was killed. That's not the case, of course. So you have many types of signals. You need to catch those signals explicitly. If you just catch keyboard interrupt, this is when the user hits Ctrl-C running it in the terminal. It won't catch any other errors that usually would occur, like when the server is crashing, it's killed by this operating system or anything else. So yeah, only useful for development. We need to actually catch sigint, sigterm, and sigup. Let's go to the next iteration. Over here, what is another problem? This is the same code that I just showed you, that if we just put all of our exception handling in this try except block, we would never catch things that happen outside. And in this case, like it is often the case that exception will happen in the very beginning. Like when you just launch your program and I don't know, there is not enough of some resource or like some related module is crashing, then it will even crash much before it runs in the try except block. In this case, like on top, highly likely somewhere on top, well, doing the imports or initiating the queue or an event loop, an exception would happen and you will not catch it. Also, in the except block itself, obviously this is like basic Python, exceptions can happen as well. So for production environments, we need to make sure that we handle these correctly. Next, I mentioned that we need to catch the operating system signals correctly, and this is like a very, very basic way to do that. As I mentioned, we catch signals sigterm, sigint, and sigup. This is a simple loop that goes over every signal and adds a handler for that. So I say here that the handler is this shutdown function, which I'll show you in a moment. The main is more or less the same, and then we run this thing, and this time we do not even need the try except block if we only want to catch the case when this thing is killed. Why am I always like speaking if this thing is gonna be killed? If anybody has this production experience, this is a problem with AsyncIO, that it runs many things in the background, not just one thing. Debugging and error handling in sequential software is easy. Like you see in traceback exactly where it crashed. Whereas in AsyncIO, you do not see it. It crashes in many times at the same time, and you have no idea how to handle that. If you do not do error handling explicitly, things will just be frozen the way they were. Imagine there are many things writing to some resources. You do not know if each of them could be completed or not unless you explicitly say what to do in case this thing gets terminated. This is why I have so much focus on this, because it's a source of pain. And the bigger your application is, the more things are scheduled in the I/O loop, the more tasks run, and the more difficult it is to track what is out there and how to handle the case when it's going to be killed in a second. And here is a shutdown handler that I promised you. This is a very basic way to ensure that something is done before the thing goes killed. So in this example, I just use the I/O loop to access all of the tasks that are running in this I/O loop, as you see over here. And I simply cancel every task. Well, this is assuming that task itself understands how it should be canceled, of course. So AsyncIO gather just make sure that all of these is handled before going to the next line. And don't forget, it's also not a case for development, but a big important thing for production, that even if you handled all of the exceptions themselves, you need to somehow log them. And this is often overseen. Like we see, again, from the sequential programming, that the main exception itself will be always logged somewhere in the console. In AsyncIO, it's not the case. You will lose it. So you need to send, like now we also have a big topic of observability. We have our different metrics that are like batched before they are sent. So we need to make sure that we flush all of the metrics that we collected to our whatever we use, Sentry or any bigger observability platform before the thing dies. So this logging info at the end, this is also something often forgotten, because if we do not do this, we will not see what has actually happened when we will do a post-mortem and researching the crash. I'm stopping the loop here explicitly, but I will show you this is not really needed. Now, this is how the main function would look after all of these changes. What is redundant here in this example? I'll just make, yeah? Correct. This is one thing. There are actually, a couple of things. So correct, the keyboard interrupt is redundant because we're already handling signals on the top. So one thing that is not needed is keyboard interrupt. Another one, the hint is here. If I run it like this, AsyncIO run main, what does AsyncIO run do? This is also often overseen because as AsyncIO was being developed, we got more like shortcuts and the commodity features that not many would actually read about. What do they do? So then I will just jump straight to the answers. So AsyncIO run handles a lot of stuff for us. It will always take the default IO loop, default currently running IO loop, and I bet nobody has, like unless we are in some debugging session, on production we would always have just one IO loop. So it takes this default IO loop and it is doing everything to manage it. So it starts it, it's ending it, it's starting it and it's closing it. So there is no need to do loop in the second line from top. Oh, I should have added line numbers, sorry. So get event loop is not needed because AsyncIO run does it for us. In every piece of software that is doing anything here with a IO loop, something like create task, we do it here on the loop. We do not need to. I'll show you in a sec. So yeah, this is one redundant thing, second redundant thing, and third redundant thing. And if we jump to the right, AsyncIO create task. This is a much more explicit and straightforward way to schedule these tasks, because it will take the IO loop itself and it will just put tasks on that one. And to make sure AsyncIO itself is managing the default loop, AsyncIO run. It will start it, it will add tasks to it, and it will close it. Let's go over this block again. So what do? We still need to create a queue, and I think we do not need to really say what is a queue. This is a very basic construct in AsyncIO. So we initiate the queue on the top, then we are handling the problems with application being killed. Then we create two tasks, putting things on the belt and getting things from the belt, using AsyncIO create task instead of loop. And we're doing this await AsyncIO event.wait. This we do instead of the endless loop. Endless loop here is not required. This will ensure that AsyncIO itself will manage to keep the loop running as long as there are things to do. This is a normal error handling, therefore I'm catching just regular exception. This is not to handle things like keyboard interrupt. This is just to catch real proper exceptions that can happen in our code. And then, yeah, finally, we always have at the end flushing the metrics, cleaning up the things. Here on the left side, I have a code for the shutdown that you partially have seen already. It's pretty much the same thing. We are not passing a loop explicitly there, but we do need to get it. So I do AsyncIO get running loop, because we then need to see which tasks run on that loop, where we are canceling all the tasks. So we do need explicit access to the IO loop here. Our final session, final piece of this session is about the debugging. What's the problem with debugging AsyncIO? This really changed over time. When AsyncIO was started, even before AsyncIO, who used Tornado just out of the curiosity? Beautiful. This was such a mess. Like when we used exceptions to propagate data, like before async await syntax, using just generators. This was code like this. Now it's much easier, yet we still are in the same problem with imagining the workflow of our application. When we debug a sequential code, we just use debugger, PDB, any really breakpoints tool like breakpoints in PyCharm. It is not possible, it's not as easy, I would say, not impossible, but not as easy with AsyncIO. Depending on the Python version you're using, you have worse or better support of default debugger in Python. If you use recent versions, and these are, I would say, 3.9 plus, you can use breakpoint normally. This is okay. It will also support the await keyword and everything. Then, some of you do not know that there is a debug mode in AsyncIO, and this is, there are many ways to run it. The one I have here is asyncio.run with debug true. Another one is just environment variables. Yeah. And it is also possible to debug it in Jupyter Notebook. I will not show it here. There are, as I say, better presentations to see debug in details. I will give you the overview. And then there are more tools how to do it. There are just two tools that I want to tell you about today. One is AioConsole. So it has asynchronous, yeah. I will not read this, so it can do input and exec and some more things for you, but the asynchronous equivalence of that, reminding you input, this is like very basic input from the console, it is a blocking synchronous operations. So it is strange that this was not available with AsyncIO itself, but with AioConsole it is available. You can get user inputs asynchronously. And it has an interactive loop running the synchronous Python console. And you have stream support to serve interfaces instead of using standard streams. Look it up online. It will give you more details. AioConsole, it's like a high-level tool for debugging. Then the final tool that I want to share with you is AioMonitor. Or in the recent Python versions, it's not actively developed, so the alternative is AioMonitor NG, like next generation. It has support for 3.10 plus, I think. So this module just adds a monitor and CLI capabilities for AsyncIO applications. The task monitor runs concurrently on to the AsyncIO loop, so not in the same IO loop. Therefore, if you block your loop of your applications, then it will still work. It works in a separate thread, so yeah. This is a screenshot how it looks like and what is the difference. As you guess from the name, AioMonitor, it's not just for debugging, it's also for monitoring. Like one of the typical situations you find yourself in while debugging AsyncIO code is you do not know which tasks are executed right now. If you run normal Python debugger, you won't see that. You will see it if you run AsyncIO in the debug mode. It will print you, well, you have to explicitly ask for it. It will also print you like all of the tasks that are executing for longer than n milliseconds. That would be usually what you're looking for, like the things that are overseen in the asynchronous code. That's it. You can also run your tasks here, of course, so use it like a normal debugger. And yeah, you need to make sure you are using the right version of this monitor if you are on recent Python versions. So I think we are perfectly in time, are we?
1 minute.
1 minute. I could sing karaoke, but I'm really bad in it. So I guess then we have 1 more minute for Q&A. I say thank you here.
1 minute for the Q&A.
Yeah. Let's go.
Okay, thank you very much and great talk.
Thanks.
Okay. These questions. Sometimes when using get event loop to run an async function, in a sync function, I get the exception no event loop, and sometimes also in a new event loop.
Sometimes also?
In new event loop.
In
if
new
you
event
want
loop,
to read the... This is the question.
When I run an async function, I get a loop with get event loop. It raises an exception, runtime error, no event loop. But if I try to create a loop, it will create a new loop.
Okay, so we cannot find or create the event loop. Exotic one. The first idea I would have is to try to run it on a different laptop or in the virtual machine. Docker. Okay, so it could be something. It could be something with the Docker environment, because event loops, they are highly dependent on the event loop of the operating system. Something like UV loop or KQ or select, depending on the operating system you use. So AsyncIO supports many of them, and it just relays things. It could be that the problem is below the level of Python. So first thing I would do is I would run a totally different container, or even just run it on another laptop. Could be fixing it, most likely would be fixing it, because all of the things with creating and listing event loops goes to the operating system. So I would look for problems there. I never seen it, to be honest, but try it. I think that could be the key.
Okay, another question. What's the usage difference between event and condition?
Event and condition. Similar, as I mentioned. Let's go back here. So conditions includes events in there. It combines, because the condition does not have the context manager. If you go back to condition, no, events do not have the context manager. So here, event is just over here, await event.wait. So you do not have the whole block that will be locked for execution for just one specific coroutine, whereas the conditions has it. This is the condition, as you see. I think with condition, and the whole part is blocked. So you can think of conditions as of a combination of event and locks. Is a simple answer of that.
Okay, clear.
Yeah, next one.
Error handling sounds like advertisement for sequential programs instead of AsyncIO. What are the best cases for AsyncIO, and when it should be avoided?
It's more pleasant to write sequential code. This can be just agreed. I mean, we can make a club of people who can say AsyncIO is confusing. It's not as confusing as JavaScript, though, and as all that spaghetti mess. So at least that part we have better. So it is confusing, and as we all have trauma debugging this callback style back from Twisted. Anybody used Twisted? Yeah, so then you know what I mean. So it's relatively, so the goal of AsyncIO, I think, was, and of the whole async await syntax introduced in Python, was to make make asynchronous programming as sequential as it gets. That was the purpose. So we have these magic words that would switch the context and stop the execution when we await something, drop the execution in another coroutine and run there and then jump back. This is all for the sake of just having less confusion. It's as close as it gets to sequential style. I think it is good. It works. I mean, well, JavaScript stole it from us, so it should be good if they did it. But there is no way around asynchronous programming in things like network events, for example. Like, this is a no-brainer, because some of you remember times of Apache, where every new network request created a new thread, and the machine ran pretty quick out of memory just because opening a thread for every request. Time of very easy DDoS attacks, when you could do that using just your one computer in like student network, crash any server because it runs Apache for sure. So there is no way around asynchronous programming if you are doing anything related to network. As well as, I would now say, now as we have more and more decentralized databases, we need to get one piece of information from one database, like will be relational database, there will be Postgres, there will be some DynamoDB stuff, there will be some blob file somewhere on S3, and we want to run it in parallel. Like, we cannot, network requests are costly. We cannot just do one after another. It will take way too much time without any reason. So we want to make these requests in parallel. If we do it in parallel, we could use threading, or using things like thread pool executor or process pool executor in Python that will make it easier for us. And still, it's too much cost for such a simple operation. So we have asynchronous drivers. We just write sequential code as we used to do, but have await in front. And that would basically do that kind of in parallel because we are waiting on the I/O. So it's important to remember AsyncIO is still a single-threaded thing. So it is not really in parallel, but because most of the network requests are just idling, waiting for the server to reply, whenever you hit this point where you are waiting for something to reply, it is probably a very good point to use AsyncIO. That's like in a glance. Yeah.
Okay, just another quick question. Have you ever had to make an existing program compatible with AsyncIO? And if so, what would you say is your most common pain point with that effort?
Oh, yeah. When we have an application that is running on AsyncIO, it's a pain to even use a library that is not compatible with AsyncIO. Even that by itself is hell. So the easiest thing that you can do, and that's a secret, throw it in thread pool executor. It's automatically asynchronous after that. So it's an easy fix. And then after you do that, step by step, you take more and more things out of the process and make you run it natively. Important things here is if you start refactoring the whole thing, never happens. Like it blocks you forever. So you need to make sure, but this is not really specific to AsyncIO. It's a general development experience that the code has to be in runnable state all the time. It's way too much effort to port existing projects 100% to AsyncIO. And even if you think it's 100%, then you will find a piece that is not ported yet. You can go in depth almost indefinitely. Things like a database. We would normally say, if you fetch things from the database asynchronously, it's done. But no, then there is establishing a connection to the database. There is error handling. There is this whole ACID thing, like rollbacks, transaction support. So if you really want to make it 100% asynchronous, it never happens. You will always find a piece of code that is not asynchronous yet. But that's not the point. The point is to port just the most costly operations. That's it. So I would say everything in thread pool executor and the things that are really costing you performance, that you implement step by step.
Okay, thank you very much, Anton. Great talk.